Welcome to the Space Telescope Public Lecture Series. Tonight's talk, Shedding Light on Dark Matter with Hubble. Our speaker is Eduardo Vitral of the Space Telescope Science Institute. I'm your host, Dr. Frank Summers of the Office of Public Outreach. And as always, I love to thank our tech team, Thomas Marufu and Grant Justice, who bring you these streaming events to you every single month. Our upcoming talks in June, we will have Web Observations of Planet Formation by Nicole Arulanthanam. All right, so the Webb Space Telescope is doing some amazing stuff in looking to see planets, and you're going to want to find out what we've found out here. This is really cool stuff, so you're not going to want to miss this one in June. In July, I will be doing the talk. I do it once a year or once every other year. And I'll be talking about our latest visualization of the pillars of creation, those famous pillars in the Eagle Nebula, showing them to you in multi-wavelength and in full 3D. We're going to fly you through them in 3D. In August, it will be year 2 in review, groundbreaking science discoveries by JWST. The James Webb Space Telescope has its science anniversary in July. And so the mission office said, hey, let's do a 2-year review. And that will be done by the principal scientist on it, Macarena Garcia Marin, also of the Space Telescope Science Institute. So if you want to find out about those talks, you can go to our website, www.stsci.edu/public-lectures, where you will find this web page. In the lower left, you'll have the links to all of our webcasts, both the current webcast and the archive webcasts on our YouTube playlist and in the webcast archive at Space Telescope. In the lower right, you can see that you can sign up for our email. Just put in your email address, hit that subscribe button. You get the 2 or 3 emails a month that remind you about our talks. Also on the website, we of course have information about each of the lectures. Here is the list of the upcoming lectures. And if you click on that lecture, you get all the description of it, as well as the links to the STSCI webcast and the YouTube webcast after it has been broadcast. For email, as I said, for the announcements, sign up at our website, but you can also subscribe to our YouTube channel, youtube.com/Hubble Space Telescope, all one word, Hubble Space Telescope. And if you subscribe there, you get our new video notices and reminders of live events every month, such as this one. And finally, if you have comments or questions, you can send them to publiclecture@stsci.edu. Our social media accounts that we run are for the Hubble Space Telescope, for the Webb Space Telescope, and for this institute itself on Facebook, X, YouTube, and Instagram. And now the news from the universe for May 2024. And our story tonight, Webb examines the horse's mane. All right, so I get to talk about one of my favorite regions in the sky. And this, you may recognize, is the constellation of Orion. And when you look in the constellation of Orion, you see lots and lots of stars, but you also see a fuzzy patch in the sword. That fuzzy patch in the sword is the Orion Nebula, which you can actually see with the naked eye. Although I will note that Galileo didn't see it. Galileo cataloged 500 stars in the Orion constellation, but he never mentioned the Orion Nebula. He had to have seen it, but he never mentioned it. Of course, what Galileo would have really, really loved is if he could have looked at the Orion constellation with special filters that pull out the gas and dust, such as this one from Deep Sky Colors. This is that same region of Orion, but with the filters for H alpha to pull out the glowing gas. And so not only can you see the Orion Nebula, you can also see the gas around the star Lambda Orionis up top. You can see this huge long arc of hydrogen alpha emission that we call Barnard's loop. And then next to the belt of Orion, you can see the Flame and the Horsehead Nebula. So this is a wonderful, wonderful, rich region of the sky. And we're actually going to talk about the Horsehead Nebula tonight. So let's zoom in and show you the Flame and the Horsehead. So up here, up in the top, next to Alnitak, which is the left star of Orion's belt, is the Flame Nebula. And then below that is the Horsehead Nebula. And the Horsehead Nebula is that dark thing pointing left to right, okay? And one thing you should notice it when looking at it this scale is that the Horsehead actually points towards that bright star, Sigma Orionis, okay? And what's going on here is the energy, the ultraviolet radiation and the winds from Sigma Orionis are streaming across interstellar space and heating up and creating that red glow along this ionization front, okay? But if we look at spin the Horsehead Nebula upright, so it looks like the horse's head, this is what it looks like in that same image from the Digital Sky Survey. All right, and so this is naturally called the Horsehead Nebula because it looks like a horse's head. This is relatively low resolution because it's a sky survey. Hubble has also looked at the Horsehead Nebula, and it gets this, which is a very high resolution version of the same thing. It's got a different coloring, so it looks green instead of red for the ionization emission here. But still, this is invisible light, and the Horsehead is dark invisible light. It's a dark nebula that you really can't see very well through using visible light. But Hubble also has a little bit of the infrared, and infrared can see more and can see through some of this dark gas. And so Hubble's view in the near infrared, this is of this exact same patch, looks like that. That's kind of cool, right? All right, because you can see that you're seeing so much more structure in the Horsehead. You're going from dark gas to seeing structure in the gas, all right, all during the heat. Plus, also, you can see that you're seeing stars and galaxies through that background stuff. Okay, so all the ionization energy that heats the gas that causes it to glow, and you can't see through it very well in visible, you can see through it in infrared. Matter of fact, actually, Hubble took a wider field view in the infrared, and you can actually get the full horse's head in the infrared. But if you want infrared, do you want Hubble? Well, not these days. All right, so what you really want is you want to see what Webb can see. And so if we go to that very top part of it, this part up here, all right, we're going to call that the horse's mane. All right, if we look in this region, this is what Hubble sees, and Webb was able to take a view of the same region, and here is what Webb's view is. All right, and so this is what Hubble sees, and this is what Webb sees, and there's just a significant more detail here. All right, and I want to point something out to you. Okay, so you see these stars here. See how pinpoint like those stars are over here? If you then go back to the Hubble, you can see how blurry those stars are. Webb has about twice the resolution in the near infrared than Hubble has. So Webb is got 2 times finer resolution than Hubble does. You can also look at the structure on the nebula itself, and you can actually see some things through the nebula in Webb that you can't see with Hubble. All right, the main part of the main is mostly opaque even in Hubble's infrared, but when you go to the Webb infrared, you can actually see things through. Plus, all these galaxies in the background, if you notice when I blink back and forth, they're kind of dim and vague in Hubble, but they pop a lot more. This is one of the things is that all these background galaxies shine really well in infrared because infrared includes the light of the faintest stars, and it picks up those faint stars, and you get to see the full structure of the galaxies. So here is the whole Webb image. all right, and seeing what we're calling the horse's mane here. And that star is not Sigma Orionis. Sigma Orionis is much, much, much further away. That's just another bright star that happens to be nearby, and it's very bright in the infrared. And you can see the 6/8 pointed diffraction spikes that tells you this is a Webb image. But what's going on is that energy that comes from Sigma Orionis and perhaps some other stars ionizes the gas. Okay, it takes the molecular gas, ionizes it, and creates what's called a photodissociation region. And using Webb's very fine resolution, we're able to study the physics of what's going on inside this photodissociation region better than we've ever been able to do before. So while the Horsehead Nebula is one of these iconic, beautiful pictures in the sky, we're also learning cool science from it with the new images from Webb. All right, our speaker tonight is Eduardo Vitral. He is a postdoc here at the Space Telescope Science Institute, and we're lovely, wonderful to have him. He told me as we were prepping this that he actually used to watch these public lecture series while he was an undergraduate in France, and now it's an honor for him to come actually be a speaker on it. And I'm really glad to have him tonight. He comes originally from Brazil. He did his academic work in France, and then after finishing it, he was one of the unfortunate folks who had to do his PhD during the pandemic. So he's actually probably really well versed in doing these online type of talks and such. And then he came directly to the Space Telescope Science Institute, where he's been working with us on his first postdoc. Now, usually I try to tell interesting stories about him, but I found out he's already got biographical material and an interesting tidbit about him in his own talk. So I'm not going to waste your time with me doing that. I'll let him do it. He can speak better than I can to that. Ladies and gentlemen, Dr. Eduardo Vitral.
Thank you very much, Frank. So let me share my screen, and here you go. So yeah, thanks a lot for the introduction. As you said, I do intend to talk a little bit of who I am in order to actually get a little more familiar with what I'm doing here. So as you said, I am from Brazil. I was born in the city that the red arrow points here, and it's called Juiz de Fora. And there I used to have access to these beautiful night skies from the southern hemisphere that you can see here. This was taken in the backyard of my hometown. And from early on, I've been a very big Star Wars fan, which I think that propelled me to be interested in space, in the universe, and that also combined with an interest in maths and physics led me to go to different places around the world. So as you said, I started my academic route in France, where I did my undergrad studies. I was lucky enough to spend some beautiful months in Hawaii on the Canada-France-Hawaii telescope, and then came back to France to do my PhD, and now I arrived here in Baltimore, Maryland, where I am in the Space Telescope Science Institute, working with amazing folks from the HST Promo collaboration, which is a group of enthusiasts of measuring the motions of stars and how these motions tell us about the galactic neighborhood, star clusters, other galaxies, how does that connect to black holes, dark matter, etc. So as you said, indeed, I was one of that was used to watch this kind of videos a few years ago, and I'm very honored to be here tonight. And I think that's a nice message to say that if you're now watching this on your laptop in whichever configuration and you aspire to one day, I don't know, become an astrophysicist, do not give up. It's very much possible. So with that, enough of chit chat. Let's talk about interesting stuff. Let's talk about dark matter and how the Hubble Space Telescope is helping us to better understand what it is. So in order to start my talk, I would like you to picture the following scenario. You're in a beautiful spring day, you're walking around, and you see a tree that is moving, such as in this image here. You might ask yourself, what is causing this tree to move? If you don't know a lot of physics, if you haven't ever think about these things, let's say you're a very small child, you might remember the Harry Potter movies and its Whomping Willow tree, who actually had its own wheel and powered by magic used to beat up the main characters. So you might think, well, the answer to that tree movie might be magic. And I'm sorry to disappoint you, but that's not the answer. We know that the reason why this tree is moving is the wind, and it's something that we can feel but just by getting close to the tree and feeling the wind in our own skin. So the big point here is to actually highlight that because you're not seeing something, it doesn't necessarily mean that this thing is not out there. It might have effects that are not visible as light to us, but we can see as making something move, for example. And indeed, this kind of thing happens in our universe. We have the law of gravity that governs the dance of the planets and stars in our cosmos, and that is actually was used by Newton to explain attraction of different bodies in our universe, why, for example, things fell down when we dropped them to the ground. And the explanation to that is basically that if you have two bodies having mass, having some weight to it, they will be interacting with each other through this force of gravity that is proportional to the mass of each body and inversely proportional to the square of the distance between these bodies. So basically what this formula tells you is that if you're put out in the vacuum with somebody you really like, well, you're gonna be feeling attracted to each other, not on sentimental terms, but on actual terms due to the gravity. And of course, here on Earth, there are other forces that just don't let us get this much close, that stop us, and they're stronger because our masses happen to be very small, not like masses of planets and stars. But in sum, that's the idea. We have here again some force that we are not seeing exactly with our eyes, but we can see its effect on other bodies, right? We can see the stars moving, and we can, for example, estimate the masses of different stars or different groups of stars due to this motion. We can, by the motion of the Earth around the sun, for example, we can measure the mass of the sun. And this kind of measurement of mass that takes into account the motions of stars due to the influence of gravity is called a dynamical mass estimate. And the term dynamics actually comes from physics whenever you have these forces interacting and generating some bodies to accelerate. So on the other side, this is not the only way to measure masses. For example, imagine that you're looking at a bonfire and on the side of it, a matchstick. You realize that the bonfire seems much more massive to be generating all that heat and all that fire rather than the matchstick. So intuitively, you could say that the bonfire is much more massive than the matchstick. Now, with the same kind of intuition, astronomers gather up knowledge about stellar evolution, about different types of stars and how they evolve, what they are composed of, and they can come up with an estimate of mass from their luminosity. That's what we call a luminous mass estimate. And it's something that allows us, for example, to say that the galaxy here in the left is much more massive than the one in the right, at least what concerns the light that we see. So, with that in mind, with these two possible types of mass measurement, astronomers like Fritz Zwicky in the early 30s asked themselves, well, what about if I compare these two kinds of measurements? So he looked into a cluster of galaxies called the Coma cluster, and he measured the motions of the stars, of those galaxies, and tried to infer from it a dynamical mass estimate, the mass that you can trace down from the law of gravity. He compared it after with the mass that you can estimate from the luminosity coming from those galaxies, and he realized that they were not the same. In fact, the dynamical mass, the mass from gravity, seemed to be much higher, such that something didn't look right. Now, he proposed back in the 30s that this extra mass that he was measuring and not seeing from the luminosity was some sort of dark mass that he coined as dark matter. Now, because the uncertainties in Fritz's study were not that great, they seemed to be very huge concerning his claims. The astronomical community at the time actually looked at it and was not very convinced. They actually put it on a shelf and waited it to see if there were any other confirmations that would arise, because that didn't seem very plausible at the time. Also, I really encourage you to go look about the life of Fritz Zwicky, who is really a funny character in the history of astrophysics. Now, with that in mind, many decades later, another astronomer came into play, and that was Vera Rubin. She was studying how the stars move around around spiral galaxies, such as the one in this image. She was interested in how to see the velocity of stars from the very center of the galaxies and how they varied as we go through the outskirts of the galaxy. And what she would expect from the luminosity is that in the very center of the galaxy, where you have all this light coming out, the mass would be much higher, and therefore the velocity there would also be higher, and it slowly decreases as you drift away from the galaxy, at least from what you can see there in the galaxy. However, once again, she compared this measurement that she was expecting from luminosity with the dynamical estimate that she measured from the actual velocities of those stars and from what the law of gravity could tell us about the mass there. And she realized that the velocities were not going down as expected. They were actually flattening up, meaning that, again, there was some sort of dark mass that was composing a vast majority of the mass in this galaxy. Now, because Vera Rubin's data was much more accurate than Fritz Zwicky, the astronomical community actually waited down and said, yep, I think that you have a point. Indeed, this seems to be some extra dark matter that we are just not seeing. Indeed, after that, some other measurements actually helped us to better understand and better confirm the fact that some matter out there just seem not to be emitting any light. Now, one of these confirmations was using general relativity as proposed by Einstein to show that light waves actually curve as they cross paths with regions containing a lot of mass, like in this image here in the left. And what people measure was that the mass necessary to bend those light rays was more massive than what we could actually observe from light. Some astronomers were actually proposing that maybe the things that we are not observing was gas that was very faint. And again, there was observations of this bullet cluster here on the top that were showing, with the help of gravitational lensing, that the gas on this galaxy was not concentrated where the actually most of the mass of the galaxy was. Most of the mass of the galaxy was actually in points where there seemed to be not enough light coming from it. And finally, one of the great victories for this dark matter model was the light that came right after the Big Bang, known as the cosmological microwave background. This image that you can see here is basically one of the first light emitted by our universe. And in order to fit those variations of light intensity that you can see here, you need to assume that your universe has more matter than we're just seeing. It has some sort of dark matter as well. So in sum, all of those different pieces of evidence helped us throughout this last century to build the idea that galaxies such as this one that you're seeing here are actually embedded in a halo of dark matter that here is represented in blue, but in reality we can just not see because it does not emit light. So again, we were observing something that was actually invisible but was having its effects on the nearby things. Now, not only it was there, but it so happens that this dark matter composes about 85% of all the mass in our universe. So really the majority of mass in the whole universe comes from something we cannot see. And that is pretty puzzling. And once you have all this kind of evidence, you actually want to try to understand what this dark matter, if it's actually a thing and not, let's say, some flaw in our law of gravity. What is the nature of it? What are the properties that it can hold? So one thing that astronomers started doing that was actually taking advantage of the very new computer resources that were appearing and the very interesting technologies that were also appearing was to build cosmological simulations that in practice try to emulate how the universe grows, how the galaxies evolve, and how the dark matter that composes part of all this mass in our universe helps this evolution, how it turns out to distribute itself throughout the universe. So you can see here is an example of a cosmological simulation with galaxies forming in these bright spots, and you have these fine lines of the cosmic web, which in reality are supported by dark matter. And one of the main things that came out from these studies of those cosmological simulations was that dark matter seemed to behave very similar throughout all galaxies. It should have actually a density profile that was very similar throughout all galaxies. Now you're probably asking, what the heck is a density profile? Well, let's go with this example here of a very crowded star cluster. If you want to measure a density profile, basically you want to measure how the density varies as you go from the very center of the source to the outskirts. So here in this case, you can see that in the center you have a lot of stars, it's very crowded, so your density of stars is pretty high. As you start going outwards, you actually start seeing that it decreases a little, it keeps on decreasing, until that you have enough points to actually trace down this orange line that is what we call a density profile. Now, in a very similar way, people use those astronomical cosmological simulations to try to see what was the density profile of dark matter surrounding galaxies. And one of the very important and most robust results of those simulations was that dark matter seemed to pile up in the center, as you can see here in this representation, such that the density profile went for a steep slope towards the center that we call a cusp. So this was what was expected from the simulations. So what the astronomers did after that was try to check if that was actually happening in our neighborhood, in the galaxies around the Milky Way, for example. And they realized while measuring their velocities and trying to measure this dark matter density profile was that dark matter did not seem to pile up that much. It actually followed a pretty much smoother, constant density profile as it went towards its very inner regions of the galaxy. And this constant profile is what we call a core, which was observed. So you can see here, there was a very big disagreement between what was expected, a cusp, against what was generally observed, a core. And that was known as the cusp-core problem. Now, how Hubble is helping us to study the cusp-core problem? Well, as I have mentioned previously, one of the main ways that we have to study dark matter is actually through the motions of stars and galaxies in our universe. Those motions trace back, due to the law of gravity, the actual mass that is sitting around whatever astronomical source that we're observing. So When you look at the stellar velocity, for example, in a galaxy, you actually have that this motion can be decomposed in 3 directions. And to facilitate the view of that, imagine you're throwing a boomerang and you notice that the boomerang does not have its common back and forth motion, but it also moves transversely to right or to left, for example. So all these 3 dimensions that we generally refer as 3D are actually the full velocity information that we need to understand the dark matter. But the problem is that so far, most of our knowledge of the universe comes from a single dimension of velocity, which is the velocity from on the direction coming back and forth from us. Are you probably asking yourself why? And the reason of it is that those are the velocities directions that are the velocity direction that is easiest to measure. We measure it through what we call the Doppler effect. It's something very similar to what happens when you hear an ambulance approaching to you and its siren seems to be getting a higher pitch. On the opposite side, when it goes away from you, you actually have the impression that the frequency of the siren decreases. So in a very similar way, the light emitted from stars that are moving away or towards us actually changes its frequency, which in light waves translates to it becoming bluer in case it's getting closer to us, or redder in case it's getting far away from us. So it changes color, and that's why we call that something is red shifted or blue shifted. It basically means that something is getting towards us if it's blue shifted and away from us if it's red shifted. Now, indeed, this is a pretty straightforward measurement in astronomy, and you just need to point your telescope to a certain star and observe with your spectrograph this measurement once, and you get the velocity. Now, why is this not enough? So in order to exemplify, imagine that I give you $100 and tell you to go buy apples and bananas. Now, this seems like a pretty big sum to buy just apples and bananas. So you're probably going to ask yourself, well, how do you want me to distribute that? Do you want me to buy a lot of apples and just a few bananas, or many bananas and just a few apples? Do you want me to buy the same amount of both? You're just going to realize that as you try to interpret this information that I gave you, which in the case is the money, there are too many possible scenarios to interpret. And in science, we call that a degenerate problem. So to exemplify this, we have here this plot, which do not really focus on the actual numbers. The idea that I want to show is basically that we have here our data represented by the black dots and many possible lines that try to fit those data. And comparatively to the analysis that I just made, the black dots, the data would be the $100, while the possible scenarios would be these lines. For example, the scenario having a lot of apples or instead having a lot of bananas. Now, the thing that gets very tricky is that in this study that I'm showing in particular here, it was shown that for these different solutions that seem to fit equally well the data, we had a very big variety of density profiles of dark matter, basically going from core to cusp, etc. So again, there are just too many possible scenarios that this one dimension is telling us. And I want to be fair to the very big efforts that have been done so far by the astronomical community in trying to extract the max of information that you can from this one dimension, and realizing that in certain cases you can decrease this degeneracy and be able to restrain things as adding more assumptions to your models. But the reality is that just one dimension is never going to be as good as actually measuring the full thing and having the full picture of what you're observing. And in order to get these order dimensions, what we have to look is not this back and forth motion, but actually the motion transverse to the plane of sky, these two extra dimensions that we can observe. Now, to observe them, what we do is basically to go at a certain point, we measure the position of a star in the sky, we come back, let's say a year later, we measure again its position. As you can see here, I'm showing that there's always some relative uncertainty related to it. You come back a little later, and you have enough points to actually see which direction the star is moving on. And from that, you can infer its velocity because you know how much time has elapsed since you first measured it. Now, the problem with that is that with the accuracy of current telescopes, if you don't wait enough time and you want to observe other galaxies, you just have too many possibilities for the actual motions that you're going to measure. The uncertainties of your data are going to be so huge that you can't really resolve how stars are moving. So again, to measure distant galaxies that are orbiting our Milky Way, for example, we actually have to wait a lot of time. And by that, I mean at least about 10 years' time. And then you can actually resolve this motion in much more detail so that you can actually try to understand how things are moving. Now that's where Hubble comes in. So a long time ago, kidding, it was just about 20 years ago, here at the Space Telescope Science Institute, a group of dynamicists that were wanting to understand better the motions of stars decided to propose different observations for Hubble to measure these motions in the plane of sky. And this collaboration is called the AGST-PROMO collaboration. And since it's been created, it has been studying different sources around our Milky Way, like globular star clusters, dwarf galaxies, or even our neighbor Andromeda galaxy. And the idea is that with those motions, we can resolve different degeneracies in modeling of the mass and of the orbits of those different objects in our sky. Now, today, I'm going to talk about a very particular source, which is the Draco Dwarf spheroidal galaxy, in this beautiful image that I actually found online by Andrew Barton on Astronomy. Now, you're probably asking yourself, Frank Summers just showed those amazing images of the Horsehead Nebula, and now you come up with this? I can't even see a galaxy here. And yes, those are my favorite objects to work with at the moment. And the thing is that there is a galaxy there, and you have to really try to see very sharp with your eyes that there is an agglomerate of stars surrounding near the center. And indeed, the luminosity that is coming to us from it is very low, such that the luminous mass that we observe from it is very low. However, when you actually look at the velocities of the stars orbiting inside this galaxy, you actually realize that you need much more mass than you're actually observing with your stellar luminosity. So that tells us, along with other dwarf galaxies that are orbiting our Milky Way, that these kind of sources are strongly dark matter dominated. And in order to resolve well their motions, not only the back and forward motions, but as I was mentioning, the plane of sky motions that are transverse to us, we actually have to wait a long time. So folks at the AGST promo collaboration have been waiting 18 years to measure precise enough motions of those skies in the extra 2 dimensions to actually be able to study its mass profile and its dark matter content. And that's the result. So this image here is actually a frame of different a video with different frames that made by my collaborator Tony Son from images of the Draco Dwarf spheroid taken by Hubble in 2004, 6, 13, and 22. And you probably can barely see any star moving. I'm gonna give you a help. You can focus on these stars here, and okay, we can see some motion there, but let me disappoint you again. Those are not the stars we are interested in. They're actually moving too fast to be actually members of the Draco galaxy. And the answer to that is very similar to this following scenario. Imagine you're trying to observe a plane that is far away, and all of a sudden a bird rushes in front of you and moves very fast. You're going to have the impression, the apparent impression, right, that the bird is much faster than the plane, which of course you know it's not true. What is happening here is that the bird is much closer to you and therefore looks to be moving faster. And that's what is happening in this galactic image. Those stars that I'm pointing here are actually like the bird. They are moving too fast because they are actually much closer to us than the Draco Dwarf galaxy. So all of that is to just show you guys how difficult it is to measure motions of those stars. Even with 18 years hoping to see some motions, we can barely see some movement. And the way we actually treat them here at Space Telescope Institute is by using not our eyes like here, but actually numbers that we have on a computer from minute motions of those stars in order to construct these extra dimensions. Okay, so let's give a quick summary of where we are before I continue. I haven't told you that throughout last century, there were actually many scenarios where people tried to measure masses of galaxies or cluster of galaxies, and they realized that the mass being inferred by the law of gravity was much higher than the one inferred by the luminosity of those sources. So that led people to propose that some sort of dark matter is lurking around and composing nearly 85% of all existing matter in our universe. Now, in order to try to understand what this dark matter is, astronomers have come up with very complex cosmological simulations that try to predict the behavior of the universe under different possible dark matter properties. And one of the things that was being told us to these different properties is that dark matter seemed to be piling up in the center of galaxies and forming a very steep density profile that we call a cusp. However, our best model of the universe so far, called the Lambda CDM, seems to fail to predict some of the observed properties of the nearby dwarf galaxies. For example, this cusp that it was predicting actually seemed to be more like a core, or in other words, the dark matter profile, instead of piling up in the center of galaxies, seemed to be rather constant. That led us to what is known as the cusp core problem. Now, part of those problems could actually be solved, or at least better understood, by having not only one dimension of the velocity, which is the back and forth direction, but the full 3D information, which we measure by adding to that the motion of stars in the sky. Now, Hubble enters in the picture by being the only current observatory that has been in operation for long enough time to resolve stellar motions of other galaxies in these remaining two velocity directions with the required precision that we need. So do not get me wrong, there are other telescopes that try to measure these motions, but usually they focus on things that are much nearer, whose actual precision is that we need to understand these things are much lower. To understand faraway objects like galaxies, Hubble is the only one who combines very high precision to a long time in operation, so we can measure those long time baselines. So back to the Draco Dwarf spheroidal galaxy. You're probably asking yourself, what has our 18 years of data told us about dark matter in this galaxy? For example, is it forming a cusp towards its center, or is it forming a core? Is it piling up all the dark matter in the center of the galaxy, or is it more spread out, constant shape? And in order to go deeper into this subject, we can actually see here how it will help us to understand better what is the nature of dark matter. So in the case you have here in the right, I exemplified how you'd expect dark matter particles to distribute themselves in a cusp case scenario. And in the left, I show how you expect them to be distributed roughly in a core case scenario. And the thing here is that you can relate that to some knowledge that we have in our day-to-day life. Like, for example, imagine that you have a glass of water and you're heating it so it's getting very close to its boiling point, but it's still liquid. You actually can look in the molecular level that the particles of water that you have in this glass will be interacting with each other, moving much faster, and more importantly, spread out, trying to loosen up from the rest of the water particles. On the other side, if you have a very cold glass of water, almost freezing, but it's still not there, then you can again look at the molecular level and actually realize that the particles of water there are going to be very tied together, grouped together. And this kind of cold and hot analogies actually can tell us about what we can expect about dark matter. So for example, in case we have a cusp, in case we have a core, then we can say that the dark matter particles are behaving like in the case of a heated water. So we can say that it's some sort of warm or self-interacting dark matter. This will tell us, for example, what are the cross sections that these dark matter particles are interacting within itself or within normal matter, which can be very helpful, for example, for scientists trying to detect particles in large scale particle colliders like CERN, for example. Now, in the other side, if you have dark matter forming cusp, which is what some of our best models of the universe are actually predicting, then you would expect dark matter to be some sort of cold particle, a kind of particle that does not interact within itself that much. Now, to the actual results of what our studies will show, I'm happy to say that they will be shared in a very near future in our official Hubble news release channel. So we are preparing a very nice release that is going to come in the near future with some information on what are our results, what do they imply for the idea of that we have of dark matter, and what can we do further on from that. Now, we are not only stopping there neither. Early this morning, Hubble was actually pointing, as requested by our group, to this very interesting dwarf galaxy. So we can not only explore Draco and look at one single data point, but actually look at other dwarf galaxies orbiting our Milky Way and try to realize how dark matter is distributed not only just in one galaxy, but in other ones as well. Further on, our team here at Space Telescope will also be looking at other dwarf galaxies with the James Webb Space Telescope. And with that, we'll add to the ongoing Hubble effort that is already mapped the star's positions throughout many years. It will add new data points that will help us to increase our time baseline and therefore our precision on these 2D motions of these stars. So with that, instead of finishing in the usual way saying that the future is very bright, I would actually say that thanks to Hubble and to the discoveries that we probably will make about dark matter, the future is going to be very, very dark. Well, with that, I thank you very much for your attention, and I'm happy to take any possible questions that you can share in the YouTube chat, and I'm sure that later on we'll get to them.
All right. Thank you very much, Eduardo. A look at very good look at the history of dark matter, and in terms of things. And I know that just about everybody uses that same image of Fritz Wiki.
It's one of the best, right? I actually did in the very first image of my slide, there's one where he's smiling, which is I managed to find, but the one that people actually like is the one where he seems to be insulting somebody, right?
He's got that finger up and everything. All right. Yeah, so this is cool stuff because I worked with Roland van der Marel on the motion of Andromeda, and he provided us with a computer simulation of Andromeda and the Milky Way, and we did a visualization of the results of the proper motion studies on Andromeda. Gosh, that was back in like over 10 years ago.
Yeah, so
Uh,
it was like, yeah, so for information, it happens to be the same group that I mentioned, the HST Promo group.
mhm.
So it
Yep.
was measurements by Roland, who is the one of the leaders, and by Tony Son, who actually helped a lot in this study of Draco. And yeah, I think it was in 2010.
Yeah, and the paper may have come out, but the time we did the press release and were able to do the visualization, I think it was a year or two later, but it was
Yeah, I mean,
it was one,
2010-ish, I would
yeah.
say.
Yeah, I was gonna say it was one of our most well-received visualizations because it involves the future of our own Milky Way galaxy,
Definitely.
in terms of that. So if what I remember from that work, when you're measuring these proper motions of these individual stars in these galaxies, they're not even moving a single pixel, right? The what you're measuring is the statistical offset as it moves, in basically some sub-pixel things. How has that changed over the years? If that was 10 years ago, is it the same sort of measurements that you're getting now, or is it even better? Because that I thought was really cool, just being able to measure things that haven't moved an entire pixel yet.
Yeah. So that's actually a great point because, first of all, what we're measuring is not like a single point. The star, although it looks like a single point when you go actually to the very fine level, it's a distribution of light around a certain region. And this distribution of light might be smaller than our resolution, which is the size of the pixel. However, the nice thing is that usually that light spreads out through a little higher region than a single pixel, so you can actually model how it varies not only by where its peak is, but how the whole distribution is moving. So yes, that's what to say that we can be able to measure tiny motions that do not represent something that looks like the same in the pixel, right? Now, to answer if that changed, well, that study used Hubble, and here we're still using Hubble. So in terms of resolution, the telescope remains the same. But we are using here uh, studying a galaxy that is much closer than Andromeda. Draco actually orbits our Milky Way. It's one of our satellites. Uh, it is still very far away for everything that you know, but it's by being much closer, it basically means that, again, if I look at two things that are distant, for example, right now, for example, you're looking in the camera, this hand here seems to be bigger than this camera, which is not than this hand, which is not the case. My both hands have same size. And the reason for that is because one is closer to the camera. Now, similarly, if you look at stars that are closer to us, like in Draco comparatively to Andromeda, then we might have things that spread a little more than a pixel than compared to what we had in Andromeda. So yeah, so things are a little easier to measure here, and because they are closer.
And the other question that comes up naturally is that this HST promo group, I mean, to do this, you need multi-cycle proposals, but these multi-cycle proposals weren't the thing back in the 2010. It's a
It is very rare to get an observation from Hubble, and what our team actually does is that it very rarely will propose first time observations, but mostly what we do is that we will scroll down the archive of observations of objects that are interesting enough and that were observed for other purposes other than measure
Mhm.
their motions. And we tried then to propose observations. For example, there was this observation in 2004. 2 years later, say, oh, let's try to measure it to measure proper motions, but it didn't turn out that good yet. So they found another scientific use for it. So we come back years later. So for example, I was telling about this galaxy that Hubble was observing early this morning. It's called Ursa Minor. It's also a dwarf galaxy, and it has been observed in 2014 uh, to for other scientific purposes. So last year, along on our team, we were looking about different dwarf galaxies who would have a long enough time baseline that we could resolve their motions and say, oh, let's propose to observe that. And then we have a case, look, there were already observations here. This is not a duplication. We want to do a new kind of science. And then if the jury that is evaluating the Hubble proposals likes it, they will say, okay, that sounds reasonable, and let's go
Yeah.
for it.
And, time domain astronomy is becoming extremely important, especially with the LSST, I guess it's now Rubin telescope coming online later this decade.
Y-
I'm
Yeah,
sorry, you want to
so
say something? Yeah, go ahead.
yeah, so basically, it's crazy, right? Because if I think like I was a child the first time these observations of Draco were obtained. I didn't know what dark matter was, and that actually tells us that science is a long-term goal thing, and it's okay. Like I'm not taking the whole credit for what's happening now. Like I'm helping a little bit with the work that I have developed, but there were all this work that was done before me that has the same importance, and yes, the other thing is that the usual time scales in the universe are much higher than whatever we have here on Earth. So for some things like orbits of planets around other stars, we might get stuff that we can measure with a reasonable amount of time, but for motions of stars that are far away or things that are orbiting, that's much more difficult, and you have
All
to wait
right.
much more time.
Okay. Well, Grant has been monitoring the YouTube chat for questions. Grant, you want to turn on your video and tell us if you found any interesting questions out there?
Absolutely. So we'll get started with we had a question or two of clarification. Um, so when you were talking earlier, the dark matter distribution, was it hot or cold? We had a viewer that missed the results of the culmination of your statement. So
So there is let me show again the slide. I think that's gonna help a little.
Yep.
thank you.
So yeah, thanks for the question first of all. And so the case here where it's hot is gonna be on the left, where you have this distribution that's more spread out. So basically, the dark matter particles are not all piled up together. And the cold case, which is like here in the left, you see that around the center you have a lot of stars that are piling up together. So when you plot your density distribution, you're going to see that forms a certain loop as you move closer to the center of the galaxy.
Gotcha.
Okay, so I think one of the questions was related to did you give your full result or are you waiting for the press release to come out? Not so you don't want to spoil the press release.
Yeah, so I did not give the full result.
That's what I thought.
I, I like, yeah, I don't want to. We are preparing a very nice press release, so I don't want to spoil things up. But I think that the point here is that what I can say is that we're actually able to say something. We have data that is not too uncertain to say like, okay, we have no idea what it is. Like we have something on what to bet. Let's say.
Okay.
Gotcha.
And when thinking about a dwarf spheroidal like Draco, it's relatively low mass, right? So my question is, when you've got a ton of stars in like a globular cluster, you can sort of assume it's in dynamical equilibrium. Are dwarf spheroidals things you know, can you assume every dwarf spheroidal is going to be in dynamical equilibrium? Have they been around long enough that everything is mixed up the way they should?
So that's a great question, and it actually opens to the other question, which is this dark mass that we are measuring an actual dark mass, or could it be whether that our models that are assuming equilibrium are actually doing something wrong, that these things are not in equilibrium? Or could it be that our law of gravity, as we know, is not completely correct? We know that it was wrong once, right? The actual description by Newton, although applicable in many ways, misses to predict some points, for example, around very close to black holes. And that's where Einstein, his general relativity come in. And some people actually believe that there is no such thing as dark matter. It's just that our understanding of gravity is not good enough and that we should be looking further into it. Now,
Yeah, but those are, I mean, that opens up a huge can of worms that does
that,
as well. It could be
it does,
anything,
yeah.
you know.
So it is definitely not the scenario that is preferred in the astronomical community, but there are people who are very good who are still looking into that. So I think that it's important to, because we have very few knowledge of what dark matter is, important to be open-minded, right? I think that if I had to bet, I would bet on it being something like a particle, given there's many other indirect evidences that we had. But it's always good, I think, to like for things that we are not yet very well sure, like dark matter. It's something that is good to keep an open eye. But coming back to your question, yes, there are some galaxies, some dwarf galaxies who are not in equilibrium, and some of our measurements of the mass could actually be due to that. Now, the
Okay.
case of Draco in particular, we have actually looked at that. There were many studies showing that it was a very like, we can't see it really well here, but it's this very round galaxy that had no like strong signs of tidal interactions with the Milky Way, or instead, there are also like people showing that its orbit was not too close to the Milky Way to be that much affected. So that's actually one of the reasons we chose to study the Draco dwarf spheroidal, is because we believe through other observations that it's pretty much in dynamical equilibrium, and therefore we can apply all of our machinery to actually understand it.
Okay, yeah, so your non-equilibrium is going to contribute a little, if there is some non-equilibrium, it'll contribute a little bit to your uncertainty, but
Yeah.
the basic,
Yeah,
the basic
so
structure.
we
Okay.
believe that the current measurements that we have for dark matter, they're much higher than what can be explained for some eventual amount of non-equilibrium in this galaxy.
Okay, Grant, Eduardo, why don't you stop your screen share? And Grant, what else do we, other questions do we have?
Absolutely. Okay, so could it be possible that dark matter is hidden relative to the observer in a higher like plane or
I
something that
remember this question.
yeah, gravitational lensing and affect the galactic mass problem? I won't pretend to know what they're talking about, but I hope you do.
Well, I didn't really understand what they mean by
Okay.
it's hidden either. It could be that, well, it is hidden in a certain way from the point of view that if you consider things that we cannot really see are hidden, right? Like the window and the trees moving that I showed. So in that sense, it's something that is hidden, but it's the way we currently understand it, it's not something hidden, let's say, behind a star or behind something that we cannot be seeing. Like if it emitted any light, we should have observed it by now. So
Eduardo, I think one of a key thing in the question was that it's hidden in higher dimensions. You know,
in
like
higher dimensions.
in string theory, they got 10-dimensional string theory,
I see
you
what you
know,
mean.
and so could the mass be hidden in a non-observable dimension
Yeah,
in
no, I
some
do
way?
not believe that is the case. It would be cool, right? But actually, we have no reason to believe that dark mass like would be like the mass is something that should be measurable in all the spatial dimensions, right? We could be look at something and not on like measure the mass like through all these directions. So there's no actual pointing towards this direction. I'm sorry.
It's okay.
We get the people who like to speculate here, and
It's good. It's always
really
good.
good.
That's how we
Speculation is
actually.
a way to come up with interesting new ideas.
Yeah, so Fritz Zwicky, when he proposed dark matter, people did not believe him. He thought he was going crazy, right? So
It's still wishy-washy depending on who we're depending on who our subject is about. We get some dark matter.
Definitely it's good to always back up your affirmations with some data.
Hey, I lived through the whole discovery of dark energy, and I was one of the holdouts who said, no, you got it. What's the phrase? Extraordinary claims require extraordinary evidence.
Yeah.
And in 1997, when people said, "Oh yes, we got dark energy," I was there, and I was just like, Yeah, you need more evidence to convince me.
Yeah.
It wasn't really till like 2003 that they got enough evidence. I said, "Oh, damn, I guess I got to accept this thing."
And
Frank's over
what
there
time until
asking
they
for
find a new
receipts.
dark something, right? That
I love it. Good follow up. Other than obviously the fact that you can see further and in significantly greater detail, how has Webb affected your work?
So for this particular galaxy that we are studying right now, and these results that we're going to soon publish, uh, it's actually not affecting at all because we're only using Hubble data. Now, for further studies, what we do intend to do in the collaboration is to actually pick up extra measurements of the stellar positions throughout time and add that to the Hubble positions, and then we can build a greater time baseline that will decrease our uncertainties. Now, there are problems with that, and mainly the main problem I would say is that we are combining data from two different telescopes that have each of them different systematics and different corrections that we have to apply to the data. So mixing them up is always a higher challenge that we are trying to do, but it's not as easy, let's say, as dealing with data just from Hubble, which is what we're trying to do right now with Draco. But we do have further programs to exploit Webb data and improve our measurements.
That was
So it
something I
occurs to
hadn't.
me that, all right, go ahead, Grant.
I was saying that's something I hadn't considered. Is the telescopes, the stations, the observing is all meant to overlap at a certain point, but also like find what others don't. But the different corrections and locations would throw all of that off, and that's
Different
something
filters, like one is observing
yeah.
mostly in the infrared, like our Hubble observations are most in the visible. So like there are different like geometrical distortions due to the shape of the mirror of each telescope. So there are actually a lot of things that happen and that we are making progress towards combining them, but it remains
Right.
extremely
And
difficult compared to using the same
you're really
telescope.
getting down to the very fine details of the data. So all of those corrections are important.
Exactly. Like we're trying to measure really things that require the precision, the maximum precision that Hubble can achieve. If Hubble
Yep.
was not as precise as it is, we would not be able to be measuring these motions. So, or at
So
least we would have to wait instead of 18 years, I don't know, 50 years.
all right. So I have a follow-on to that because when we think about Webb, of course, sees the lower mass stars in the infrared. The low mass stars shine brighter in the infrared than they do in visible light. So getting those low mass stars, which there are more low mass stars than there are high mass stars in any galaxy, that seemed to me like if you had that same 20-year study with Webb, i.e., if we waited till 2040, you would get finer, you would have more data points or
Yes,
with just a
actually,
slightly better resolution as well.
yeah, so that is something that is actually being done right now, not only for these dwarf galaxies, but for objects that are closer, and therefore we can build already proper motions with what Webb has. And people are actually being able to detect not only low mass stars, but even like brown dwarfs, which are basically in the intersection between what a planet and a star is. So people have been measuring those in globular clusters. There are a few studies that actually came this week, and yeah, because Webb can pinpoint these very low mass stars, it has a very good potential. So Webb has just been launched, but I'm sure that as it keeps on, people will be trying to build proper motions with it as well. There will be proper motions that are not only just combining data from Hubble and Webb, but only Webb and Webb proper motions. And later on, when Roman arrives, then you're going to have another great revolution due to its great field of view that is going to be help us to measure not only small patches of galaxies, but the entirety of the thing.
All right. Okay, Grant, do we have other questions?
Absolutely. So let me let me just start reading this one.
Okay.
Um, are you familiar with the newly discovered galaxy JO613 plus 52, which has an HI mass of around 109 M-sun, yet lacks the optical counterpart. It's apparently bare dark matter in mass without ordinary matter, and the measured hydrogen is insufficient to account for the total mass.
Okay,
I
so they're
am not
talking.
familiar about this specific galaxy. I'm sorry. There are many galaxies out there, so there are some which have very famous names of constellations like Draco or Ursa Minor. But for those that have some numbers like that, they're usually the numbers are basically the position, stellar coordinates of them. And
Right.
I don't recall knowing this galaxy, but yeah, some galaxies they seem to have H1 mass, which is basically the mass that you measure from a certain patch of the luminosity of the gas. That is smaller than what you can account for its motions, right?
Do we have any idea as to why? Do we have suppositions, or is it something that we're still actively investigating?
So just to confirm that I understood the question, the person was saying that there was more mass from coming from motions than from the luminosity. Is that it, or is it the opposite?
Um, a HI mass of 109 M-sun, but it doesn't have the optical counterpart, meaning that there is.
I mean, this is a galaxy that's just H1, just a hydrogen blob without stars is what
Oh,
they're implying here. I
Okay.
mean, this is like a very, very low surface brightness galaxy. If the H1 mass is 10 to the ninth,
question.
10 to the ninth M sun is what they're trying to say, not 109 M sun. I think
Okay.
they're trying to say that there's a billion solar masses of hydrogen there, but no optical counterpart. So,
I'm thinking they're saying that the mass, the measurable mass doesn't line up with the observable mass, or at least that was how I read it.
Yeah, I'm not really sure what they meant. Like the fact that there's no optical counterpart doesn't actually pose a problem per se, right? The web, for example, something that does not have an optical counterpart, and still we're able to measure a lot of things with it. But yeah, I didn't really understand if the question was if there was some inconsistency or if I was aware of the galaxy, which I mean, sorry again, I'm not.
No, you're fine. I'm asking for
Yeah, yeah.
clarification in the
No,
first
right. I
sure.
place.
guess they're wondering if, if you've got an H1 cloud, could that H1 cloud have dark matter that helps hold it together
Oh,
when you don't see any stars there in that H1
okay.
cloud?
So in that sense,
Something
our
like that.
current picture of the universe is that galaxies in general, they form around inside clumps of dark matter that collapse. So I don't know about, so if it has 10 to the 9 solar masses, it is, and it's coming from luminous matter, then I would say that it's something that seems very big, right? So I don't know if it would be considered as a galaxy having how many stars does it have, but I would say that just with those information it was given, looks like something that could be surrounded by dark matter. Yeah.
Yeah, I mean, the whole field of ultra low surface brightness galaxies has taken off a lot over my career
Hmm.
because there were just a few low surface brightness galaxies, and now we have so much better techniques for finding them um, that it's intriguing to see what's out there, and I guess
Yeah, there are
if
many stars.
there's no motions, if there's no stars to find motions, you won't be able to measure the dark matter. I guess is one of the questions that spurs in me. But go ahead.
So you can actually measure motions not from the ones like that you're measuring from stellar motions. You can actually measure sometimes from the gas from, again, like similar for using Doppler effect because you have the light. So but that's like one thing, right? Uh, Now it's true that there are a lot of galaxies that have been discovered only recently. Most of these dwarf galaxies, like even Draco was one of the first dwarf galaxies to be discovered, and it was discovered in 1955. Which, if you think in the history of how much time we have been observing things in the sky, it's pretty recent. And recently there were dwarf galaxies that with only like 10 or order of 10 stars, which is really like very small amount. So yeah, we have been discovering a lot of things, and I think that a lot of discoveries are gonna come from finding out that those low surface brightness galaxies are there. So
Okay, I
yeah.
got some clarification. Hopefully, this will help. He's talking about hydrogen emission Doppler signals, 21 cm HI emissions.
That's it. That's the H1. Yeah, we know about that. We got that. Okay.
Yeah, so the H1 they can because they are Doppler emissions, we can infer velocities for them. Actually, what discussed core problem, one of the places that it was actually resolved per se is that for galaxies that are rich on on H1, and they were explaining that because you had a lot of stars there and this gas was surrounding, you could have had at certain point supernovas that, due to their huge impact, they could have depleted the center of the galaxy from dark matter, such as in a cusp scenario. So people have been studying dwarf galaxies that have H1, and you can measure your velocity from it. But the kind of ones that we're doing here, we're actually looking at not the gas motion, but actually the stellar motion. You cannot do proper motions with gas. You can just do this kind of Doppler shift thing.
Right.
Makes sense.
Okay. And I have to ask, do you know a Professor Lucas Fagundes?
I was
Lucas
about to end on
Fagundes,
that
oh,
one.
I do know. He was my chemistry teacher.
Yes, he's very happy to be watching you tonight.
Oh, thanks
He's
to know,
watching
Lucas.
this here, and
Yeah.
he made a comment in the chat, and I just wanted
Oh,
to let you know that
very happy.
your
Yeah, he was
former
my
teacher,
chemistry teacher in high school. Yeah,
your high school teacher, is very happy to be able to watch you tonight.
I'm very happy. I feel very honored.
All right, Grant, do we have a last question for Eduardo?
That about does it for the chat. You are welcome
Okay.
to finish out if you would like.
I don't have another question. I think I've thrown all going through my notes. I think I've covered everything that I had. All right. Thank you, Eduardo. This has been a fun discussion of things that we can't see and how can we tell they're there. Ladies and gentlemen, come join us next month on June 4th. Web observations of planet formation. Looks to be a great talk. We hope to see you there. Thank you for listening.
Thank you very much, Frank, Grant, and Thomas. Again, it's been a huge honor for me to be here. And good luck following it up.
All right. Thank you. Happy to have you.
And you're good.
All right.